So now this video discusses about the waves as well as the energy. Let's say if we have the atomic structure. Let's say this is the nucleus that contains the neutrons as well as the protons. And we understand that the outside the nucleus we have what to call them as the energy levels. And let's say this is energy level number 1, I'll call it as N1, and I'll call it as N is equal to 1, meaning energy level 1 should be N is equal to 1. And let's say we have the energy level 2 that I'll call it as N2. Let's say that is the case. And let me have another energy level, I'll call it as, let's say, energy level 3. Let's say that is the case. And of course, we may also have the energy level 4, 5, and so on, like that. And we understand that according to the principles of the electrons allocation, that is the electron configuration using KLMN notation, first shell must have the maximum number of 2 electrons, and the second shell must have the maximum number of, should be 8 electrons, and the third shell must have the maximum number of 18 electrons. And from the basis of the formula that states that the maximum number of electrons, so maximum number of electrons in a particular actual energy level has to be given as 2n squared, where n represents the energy level. And for that case, energy level 1 will have it as 2 times 1 to the power 2, that is given as 2. Therefore, the maximum number of electrons the first shell can hold will be given as 2. And likewise, for the energy level number 2, we just have to substitute, you have it as 8, and so forth, like that. Now, there are some cases you should have to understand that in the particular actual energy level, electrons are able to rotate about. Electrons are able to rotate within, I should say, electrons are able to move within their energy level. So which means in the first shell, electrons can move around the nucleus in their shell. Likewise, in the second shell, electrons can also be able to move actually in their actual energy level. But also in some cases, the electrons can move from one energy level to the another energy level. That is possible on a condition such that whenever the atom has been energized. So whenever the atom has been energized, it means the electrons will gain kinetic energy, then they'll move from one energy level to the another energy level. That's what will happen. And even whenever the energy has been drawn from an atom, electrons will move from one energy level to the another actual energy level. So let's consider the case in which the electrons has moved from lower energy level to the upper energy level. Now let's say we have the energy being applied on an atom. So electrons will move from lower energy level to the upper energy level, like that. And likewise, if the energy has been drawn from an atom, electrons will move from upper actual energy level to the lower energy level. That's what happened because the electrons will have lower kinetic energy. Therefore, they'll move to the lower energy level when the energy has been drawn. And when the electron has moved to actually upper energy level, we say it is in exciting state. We call it as exciting state. That is when the electron has moved from lower energy level to the upper energy level. We call it as exciting state. Exciting state. That is when the electron has moved from lower energy level to the upper energy level. And whereas when the electron moved from upper energy level to lower energy level, we say it is at the ground state. So keep that in mind. It is at the ground state where the electron has moved from upper energy level to lower energy level. So it is possible for an electron to move from, let's say, a third energy level to the first energy level, and even from 15th energy level to let's say third energy level or second energy level, and sort of much as the energy has been removed from atom, or the atom has been energized, where the electron moved from lower energy level to the upper energy level. Now what happens whenever the electron is changing the energy level? So whenever the electron is changing energy level, there is always what we call as the spectra. That is something more or less like light in form of wave that is being always emitted. So always we call them as electromagnetic radiations that are being emitted whenever the electron is changing the energy level. And these actual waves carries the energy along with them, which is denoted as E. That is the energy, and these actually electromagnetic waves carries as they are being emitted. So whenever electron is changing the energy level, there is always electromagnetic radiations that are being actually emitted along the process. And these actually electromagnetic radiations, they are actually in form of waves, and they are of different nature. And for the sake of interest, we have different actual waves that are being emitted along. And we have what we call them as gamma rays. It is possible to emit the gamma ray as well. So we do have what we call as the gamma ray along. So we do have what we call them as the gamma rays that are also being emitted along. And we do also have what we call them as X-rays. We do also have what we call them as X-rays. We also do have what we call them as ultraviolet, or we call also them as ultraviolet, whatever the pronunciation. And we also do have what we call them as infrared. So we also have what we call them as infrared. And we also have what we call them as microwave. We have what we call them as microwave. We also have what we call them as radio waves. We also have what we call them as actually radio waves. And there's some other actually examples of waves that you can come across. But these are the actually typical waves that are being emitted along as the actually electron is changing the energy level from one energy level to the another energy level. So keep that in mind. And now how can you be able to have, let's say, the frequency of the emitted waves? Let's say that is the case. How can you have the frequency of the emitted waves if that is the case? Now frequency, which is symbolized as actually V, it is given as a speed of light divided by the wavelength. And of course some books, they will present the frequency given as F. It doesn't matter. And of course the frequency is given in hertz. So frequency is given in actually hertz. So that's the frequency. It's given in hertz, and the speed of light is always constant, and which is given as, speed of light is given as 3.00 times 10 to the positive 8 meters per second. And the wavelength, basically, it is given in meters. Let's say it has been given in whichever unit, it have to be converted to meters. And demonstrate it is expressed in nanometers, but it is your humble duty to express it to be in meters, and basically like that. And how about the energy in which the waves carries along with? The energy is given using the Planck's quantum theory, which is this: the energy emitted is given as the Planck's constant, which is given as actual h times the frequency, which is given as v. So which is the same as having it as the Planck's constant times the speed of light divided by the wavelength. So this is how we can have the energy emitted along the way. So which means if we have the energy emitted, and if we have, let's say, since these are the constants, we can be able to have the wavelength. Likewise, the energy can also be, likewise, if we have the actual wavelength, and we have the speed of light and the Planck's constant, we can be able to have the energy. And what is the value of the Planck's constant? So the value of the Planck's constant, basically is given as, Planck's constant, is given as, should be 6.63 times 10 to the power negative 34 joules per second. And by the way, energy has to be given in joules unless otherwise. Let's see how we can apply that in the following questions and appreciate. And now let's say this is the question. The wavelength of the green light from a traffic signal is centered at, that is the wavelength, that is lambda. We have it as, it should be 522 nanometer. So nanometer. Of course, it has to be in meters, where I just have to substitute the value of the prefix nano. We'll have it as 5 times, should be 522 times 10 to the power negative 9 meters. So that is in meters. And now the question says that we should have the frequency of the of the radiation. So what is the formula? We'll have the frequency being given as, speed of light divided by the wavelength, and of which the speed of light is constant. It is given as 3 times 10 to the power positive 8 meters per second. And from there you can be able to have the frequency. Likewise, we can also have the energy that is being given as the energy is equal to, Planck's constant times the frequency. Upon having the frequency, you can put it here, and we have the Planck's constant being a constant value that we can have to substitute and have everything what went there. So that's how you should have it. So Planck's constant, by the way, it is given as, should be 6.6 3 times 10 to the power negative 34 joules second. So you can have it there, then be able to substitute, and we'll have the frequency in hertz. So frequency is given in hertz, so you have it like that. And that can also be given in actually in second to the power negative 1, since it is given as 1 minute, actually 1 minute per second. It can also be expressed as second to the power negative 2, but basically it is given in hertz, so you should have to prefer using hertz. And now let's have the question: what is the wavelength and the energy of an electromagnetic wave whose frequency is that? So we are looking for the energy and also the wavelength, and are given the frequency, which is given as 3.64 times 10 to the power positive. By the way, this is per hertz. How should you have the energy as well as the frequency? Should be wavelength if that is the case. So the formula for the energy is given as HV, which is the frequency. You can put it here and have the energy. And the wavelength is calculated from the formula for the frequency. And much as the frequency is given as the speed of light divided by the wavelength. So wavelength will be given as speed of light divided by the frequency. You can be able to have that. So that's how you start to understand about the concept behind the waves as well as the energy. So different waves are emitted whenever the electrons are changing energy levels from one energy level to the another energy level. So keep that in mind.